Dr. Saurav Chakrabarty, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. In the last lecture, we had seen graphs and its some applications. So, today we will be looking at the connectivity of graphs, and then we will be looking at the depth first search algorithm. So, to recall, a graph is given by a set of vertices v, v1 to vn, and a set of edges. Edges are a set of pairs of vertices. Now, a graph is given as G, which is also given as v comma e. V is the set of vertices and E is the set of edges. If uv is in the edge and vu is also in the edge, then we call the graph an undirected graph, and a weight can also be assigned to an edge. In that case, we call it an weighted graph. If there is an edge between u and v, or rather edge from u to v, then we say that v is a neighbor of u, and the total number of neighbors a particular vertex is called the degree of the vertex. For example, here we have a set of vertices. We always represent vertices as some circular nodes in the plane, and each of these edges, since they are just edges are of size sets of size 2, so they are represented as lines. So, for example, here there are edges between A and D, and there is edges between A and B, and that means that edge AB is there and there is AD is there, but this edge say AC is not there. B is called the neighbor of A, similarly D is a neighbor of A, and so on, and the degree of A is the number of neighbors it has, which is 2. Similarly, degree of D is all the neighbors it has, which is 4, and so on. As we told, we can also have weights on these edges. For example, we can have weights like this, which basically means that this edge AB has a number 7 assigned to it. Now, what does the number 7 describe? That depends upon how we want to interpret it, and we will see it later on how to look at it. And we can also have the directed graphs. That means, if A might be related to B and B is not related to A, we denote it by the arrows. So, we have this arrow like this. So, D has related to A, there is an edge between from D to A. So, A is a neighbor of D, but there is no edge from A to D, the arrow is not going this way. So, D is not a neighbor of A, and in such situations the total number of neighbors like this and the neighbors D A, D B are the two neighbors. These are called the out degree of the vertex D, how many edges are going out, and how many edges are coming in to D, which is in this case is 2, is called the in degree of this vertex. We had seen all of them in the last lecture. The advantage of this looking at graphs is that, first of all, it is a very mathematical way of expressing relationships among objects. It is something that we have to do in many real life applications as well as computer applications and so on. This way of representing graphs is a very simple and general technique. Many problems in real life can be designed as problems in graph theory. We saw some examples of it in the last lecture, and therefore, studying the structure of graphs and designing algorithms for graphs is an important field. In the last lecture, we did also look at things like coloring of a graph and the independent set. Today we will be looking at much more basic concept called connectivity. So, before we define connectivity, we have to define something called a path. So, here is a graph. We have the set of vertices and these edges are there, and we say that, say, consider these two vertex G and A, and we want to look at a path from G to A. What is a path? Think of yourself that these are nodes, there are intersections in a city or there are houses in a city, and these edges denote roads. So, you are in a road, a node G or a house G, and you want to go to a house A. How will you go? You can take an edge and then another edge and then another edge and then another edge and then another edge and so on. So, path is something like this. Say, here is a path. From G you go to F, from F you go to D, from D you go to A. If there exists such a thing, then we call that there is a path from G to A. There need not be a unique path. For example, this is a path, at the same time this is also a path. This might be slightly longer path as such, it looks like, but still it is a path. It is like from G to E, E to C, C to B, B to D, and then D to A. So, this defines as a path. So, we say that if there is a path from G to A, we mean something like this. Now, when the edges are not undirected, but they are directed, for example, in this case, say I have put directions on these edges, in that setting things become a bit more interesting. So, there it is like a one way road, you can go on this road, but you cannot come back. For example, here from G to E you can go, no problem. From E to C you can go because it is a directed line. From C to B you can also go, but B to D is a edge which is going in the opposite direction. So, there is no way one could go from here to there, B to D. So, this is not a valid path. So, this particular edge there is a problematic edge. So, in this case we get something say like this, and this is what we call a directed path. It is a path on a directed graph. So, again we say that there is a directed path from G to A if such a path exists. So, in an undirected graph, if between any two vertices, if there exists a path, then we call that one a connected graph. It is something like you are living in a city, and if from any point to any point you can go by walking, then it is called a connected city. But if say in your city there is a river going through it and the river does not have any bridge, then how will you go from one side to the other side? In that case, it is not a connected city. So, similarly, if between any two points there exists a path, then we call it as a connected graph. And in an undirected graph, note that if there exists a path from U to V, then a path from V to U. So, an undirected graph is a path without any direction. So, it is not a one way traffic at all. So, of course, if I can walk from my house to your house, then you can walk from your house to my house. So, if there is a path from U to V, there is a path from V to U. Now, let us look at all the in a graph, say if it is not connected, then look at all the vertices that are connected to U. So, say U is a vertex and all the other vertices that are connected. For example, in the case of say you are living in a city and there is a river going through it and there is no bridge on that, then all possible edges, all possible vertices in the south side of the river is connected to you. So, this set of vertices is called the connected component of a vertex. So, it is all the vertices which are connected to a vertex, and it is not hard to see that a graph can be written as a disjoint union of connected components. So, typical problem that one can ask is this graph connected? For example, we looked at the friendship graph in the last lecture, where we look at this Facebook users and we draw an edge between these two graphs, any two profiles if they are friends with each other. Now, it is a natural question to ask is that is it all connected? Like, is it that if I am a person sitting in India and somebody else is living in middle of Africa, is there a path or set of friends such that I know someone, that person knows someone, that person knows someone, and so on, and then that person, the other person will know the person in Africa. So, whether this graph is connected is a very important question to ask. It depends upon whether a society is completely disconnected from the rest of the society or not, and so on. So, this is something we need to answer again and again in many other areas of problems. One can even ask more complicated questions like, if I remove an edge, will the graph still be connected? For example, if you have a city and you have a river on it going through it, and there is one single bridge, over the river, and the natural question to ask is that if that bridge somehow breaks down, will the city still be connected or will it be disconnected from the rest of the world? Of course, we need to answer this kind of questions. There is another concept that we want to talk about, is called cycles. So, what are cycles? So, cycles are a set of paths which look something like this. So, here is a cycle. It looks like a cycle because you start walking from G, G to E, E to B, B to D, G to E, E to B, B to D, T to F, and F to G. So, you walk on a path and you come back to itself. So, this is called a cycle. Cycles are very interesting objects in graph theory also. So, here is another cycle, and in the case of directed edges, again this path that we have to take has to be directed. For example, this path E to B, B to A is fine, but A to D is not an edge. So, this cannot be a cycle. But here I can go from G to F, F to E, and then E to G. So, this gives us a directed cycle. A graph that does not have a cycle is known as a tree. Now, one might think that why are we defining such a weird name for tree? The reason is that if a graph does not have a cycle, it looks something like this. It has some, you will see on some time that it will look something like this. It looks like this is called the root of the tree, and the rest of them are called the branches. So, it is like you can think of it in the opposite direction, where I make the root as the bottommost thing, and then everything is like a branching that keeps on happening. So, this one and this one are same, and that is the reason exactly why this is called a tree. A graph that does not have a cycle looks somewhat like this, and therefore, it is called a tree. The trees also have lots of other characteristics, but for example, here is a tree, and say this is a tree that does not have any cycle. Similarly, this is another tree, and note that this trees are such that this tree touches every vertices. Even if you just look at the red edges only, even then this graph will be connected. So, connected undirected graph which does not have a cycle is called a tree. A tree always has v minus 1 number of edges. A tree that touches every possible vertices is called a spanning tree. Spanning trees are very important objects again, which helps us to understand how the graph looks like. And it turns out that every connected graph has a spanning tree. So, one problem that one would like to ask is that given a graph, check if it is connected. Given a graph, check if it has a cycle. Given a graph, find the spanning tree. These are the three basic questions in graph theory that can be asked, and all of them will be answered using something called a depth first search. We will take a short break now. After we come back, we will look at the depth first search. Welcome back after the break. Before the break, we were talking about problems that can be asked in graph theory, which are typically, is a graph connected, does a graph has a cycle, and given a graph, find a spanning tree of the graph. And we told that depth first search is a solution to all of them. So, let us understand what a depth first search is. It is an algorithm that will find a spanning tree. After that, we will try to analyze how we can answer the other question. So, here is a graph. So, we start with a stack. A stack is an object like this, like a pile of books. You can put something on top of it, and you can remove something from the top. You cannot access something in the middle. So, everything happens at the top. So, first of all we have to understand where do we want to start from, or what is the root of the graph. So, here we are, let us look at A. A is the first vertex. So, we color this one red just to indicate that this is the first vertex, and we put that vertex at the bottom. Now, we look at all its neighbors and pick any one of the neighbor. Say B is a neighbor. As soon as we find a neighbor, if that neighbor has not yet been colored blue, so in this case it was gray, then we color it blue and put that vertex in this stack. Now, we will look at the topmost element in this stack at any point and look at its neighbors. The topmost element here is B, and look at its neighbors. Let us find one neighbor of B. E is the neighbor of B. Now, E was again not blue, it was gray. So, gray basically indicates that this vertex was untouched. Blue indicates that this vertex has been touched. So, this has been touched, and we put that edge, a vertex E in this stack. Now, again the next step we look at the topmost element in the stack, which is E, and I will look at E and it is for neighbors. We can pick any one of the neighbors, and we said pick one of the neighbors, which is say C. Again C was untouched before, so we touched it, we looked at it and we put it in C. The next thing is we look at the topmost element of the stack, which is C, and say that okay, what is the, let us take a neighbor of C, and this was B. Sadly, B has already been touched, therefore, B has been colored blue. So, if B has been colored blue, I would not take this edge, I will color this as a different color, we will reject color and leave it like that. The idea is that we are trying to generate a spanning tree of this graph. A spanning tree cannot have a cycle, because a tree cannot have a cycle. So, if I had picked up this blue edge, then I would have got a cycle immediately, I would have got a B, E, C, a cycle, because we have come from to C through some path, and now here is another edge that I can see. So, I will get a cycle. So, in that case, if I see a new a vertex which has already been colored blue, I discard this edge, in this case I basically color it blue and do not do anything. Then again we look at the topmost element in this stack, which is C till now, and look at its other neighbor. Now, what is the other neighbor? Other neighbor is H. Okay, H is untouched, and we look at it and we make it blue. Now, again we look at the topmost neighbor of H. Now, H does not have a single vertex which is a neighbor of itself. So, basically we are done with H. From H we cannot go anywhere. If such a thing happens, we will pop this H out, remove this H from the top of the pile and color this H green. Now, again we look at the top of this stack, it is C. Now, C had two neighbors B and H, and we have checked both of them. Since we have checked both of them, there is nothing more to check. So, again C is done with. So, we will remove C and color it green. We come to E, top of the stack. Now, E, we have seen this vertex C, but there are other neighbors of E also. So, we look at the other neighbor of E, say F. F is untouched before, so we put F in this stack and we color F blue. Now, again we look at the topmost neighbor F, and we see that pick up one neighbor of F, say which is D. Now, D is also untouched and we color it blue. Now, we look at the topmost element in this stack and let us look at its neighbors. First of all, we look at its neighbor D A. Now, A is not gray, that means A has been touched, and therefore, I cannot take that edge, I will have to discard it. Again I look at D B, same thing, I cannot touch this, take this edge, because B is already looked at, and similarly E. Now, once we are done at this stage, D has no more neighbors to check. Once D has no more neighbors to check, we again pop it out and color D green. We come back to F, look at its neighbors of F. Now, D was checked for F, but G was not checked. So, we check for G, put G there. Again we look at the topmost element of G, topmost element of the stack, which is G. Now, G has a neighbor which is E, but E is again already touched. So, E is done. So, we have to pop G out and color it green. We look at the topmost neighbor of F, topmost of the stack, which is F, and F we have looked at all its neighbors. So, we are done with F. We pop out F and color it green. We come to the next one, which is E. Again we are done with E, and then we come to B, and again we are done with B, and so on, and finally we go remove A first. So, now see, we have done a procedure. After this whole procedure is done, the stack again become empty. The edges have been split up into two parts, the red and the blue edges. Note that these red edges has been so chosen that they do not form a cycle. At the same time, they form a spanning tree. Why do not they form a cycle? They do not form a cycle because if a cycle existed, at whenever the last edge was to be chosen, I would have understood that the earlier vertex has been looked at, and I would have discarded, not taken it. For example, when I was looking at D, at that time we had seen BE, we had seen EF, and we had seen EFD. Now, if we had chosen DB, we would have got a cycle, but since I know that D has been already been touched by the color of this node, so we look at that. Since it has been touched, so we do not take this edge. So, this ensures that we do not ever make a cycle in this graph. At the same time, we touch all possible vertices. So, this is called the depth first search algorithm. Why is it called depth first search? It is called depth first search because it is like you have a maze of things. You have a whole city in which you are looking for particular object. So, what can we do? We can just run in one direction till we hit a dead end. When we hit a dead end, we come back and look for whenever we can find out. So, it is exactly like this. We kind of ran from A to B, B to E, E to C, C to H. We did not even think about whether there was a neighbor of E or not. We just ran till we hit H. When we hit H, we realize, oh, okay, now we are dead end. So, let us come back. C. Okay, again we are dead end, come back. Then we said, oh, okay, from here it is still not dead end, and we again ran F to D. At D again we realized that there is nothing else to do. We retrace our path to left, we looked at G, we found that G is the dead end, and then we kind of retrace back. So, this is why it is called depth first search. We basically run on the depth of the tree as much as we can, or depth of the graph. There is an equivalent algorithm called breadth first search. We will talk about it after 2 lectures. So, now this is the algorithm that we have. So, we have used this stack crucially. The stack is a very useful data structure to have. It is a simple data structure. It allows for 2 operations. The first operation is called the push operation. Push operation is it pushes some object on top of it. So, or in other words, it is like the pile of books I talked about. It takes a book and puts on top of it on the pile, and it allows a pop operation, means it does not allow you to look at the books in the middle, it just allows you to look at the topmost book. So, it just pops the one from the top, and that is it. Now, recall that in the last example that we did, that is exactly what we were looking at. We were looking always at the topmost place in the stack and making some decisions, and if we have to put in something, we are putting it on top. It turns out that both of these operations can be done in O of one time, or in other words, in constant number of steps. It is just some simple linked list operations that can be done. Now, once we have this stack, we can have our pseudocode. Pseudocode is again simple. We have this stack, it is initially empty. We color all the vertices gray. We push the vertex from which we have to do the DFS. So, it is like DFS of g comma v. So, we have been given the graph g and the vertex from which we have to do the DFS, which is v. We have given g comma v. We push the vertex v into this stack, and as long as the stack is not empty, what we do is that we look at the topmost element in this stack. If the neighborhood of u is empty, then that means we have hit a dead end, and then we color it as green, as if we are done with that vertex. Else we take a w from the neighborhood of u. If the color of the w is gray, then means it is untouched, then we will do various operations. We will first of all we will color that one blue. We will select that vertex edge uv. Since we have taken the last element, so we will putting that last element back, and we will also putting the new element back into the stack. And other thing is that we will remove the w from the neighborhood of u. This is just done so that we do not come back to the same vertex again and again. Like once we have seen one, we were at u and we have seen w, means I know that I have gone through this edge u w. So, I do not need that u w. So, I can just remove that vertex v w from u, u's adjacency list. So, in some sense this helps us ensure that no edge is looked at more than once or actually twice. So, for runtime each edge is visited at most twice, one for each vertex. So, I mean that if there is an edge between d and e, I first look at between d to e. Once I have done with that looking at from d to e, I will remove that edge from e from the adjacency list. Else we will be at later on we will be looking from e to d, which will be again we will look at it only once. So, for every vertex edge we will look at most twice. Each vertex is visited at least once. So, the total runtime is order v plus e. Recall that the adjacency list, which is the one of the most concise way of representing a graph, also had input size order v plus e. So, what are the applications of this DFS? See, at the end of the DFS, all the vertices are colored green. If a vertex is not colored green, that means that I have not reached that vertex, or there was no path to reach that vertex from my v. So, if all the vertex are colored green, that would imply that the graph is connected. So, this is a very easy way of checking for the connectedness of a graph. Also, if at any point of time I had encountered an edge that is to a vertex that is already seen, then that would give me a cycle. I described it earlier also. So, as soon as we encounter such an edge, we can say that, oh, I have got a cycle. So, this is also a simple way of checking if a cycle exists, and also it gives us a spanning tree for this graph G. So, this comes to the end of the lecture. We looked at some definitions of paths, cycles and connected components. We looked at trees and spanning trees, and we looked at the depth first search algorithm for finding a spanning tree. We will come back next lecture to look at more applications of depth first search algorithms. Thank you.